Right. So, as I said, I'm part of the Leeds iGEM team. I'm also an undergraduate physicist, so I'm probably getting on to what iGEM is. So, iGEM stands for International Genetically Engineered Machines. It is a foundation these days, and it's a competition. So, the foundation maintains the registry of standard parts. We'll get into that in a moment. The competition is yearly, and originally started out between three divisions, so undergraduates like myself and different university teams competing with each other to produce synthetic biology products. They also have a high school division. They have one for professional labs. They will soon be creating one for next year for DIY labs and bioassays. So it's kind of why it's quite essential to everyone here if you're interested in doing this, something you want to get into. So as Lawrence already said, synthetic biology is the idea of redesigning things and everything else. So within iGEM, there's a broad spectrum of projects, there's all sorts of projects to get involved. But they all end up using very similar principles, which is this thing here, parts registry. The idea behind parts registry is to simplify down what you're using and make it standardized and make it a lot easier to use with presentation of different things. So here we have literally a catalogue of promoters, rather than binding sites, protein domain, protein coding sequences, translation units, and so on. These are all just different bits of DNA that do different things. It's kind of best to sort of think of it as electronic components to some degree. So promoters are effectively switches to turn something on to start transcribing DNA and cause something to be produced. Rather than binding sites that are just necessary in general to allow things to actually do it properly, it needs to be there for something. Protein coding sequences produce things like the proteins that Lorna works on. And then of course we have terminators which tells us stop. You can basically write a program with the DNA code. These are the different bits you need to use. So what iGEM does is they maintain this registry, and every year the teams that come together have to submit new bioscripts that they've designed. They don't always work necessarily, but others are free to improve on them. They now have a very, very large number of them, somewhere in the region of 5,000. In fact, last year 1,500 new bioscripts were added to the registry. But the point is, they're all meant to be inserted in the same manner, or all put together in the same manner. So it's no longer a case of genetically engineering something is something you have to know exactly how PCR works and exactly how you're going to cook this one thing or anything else. There's a much more standardized procedure for it. It's a very much more standardized and regulated way of doing it. And in that respect, it's kind of like Lego bricks now. You can actually take each brick out from one section and pop it in. So that's what iGEM offers. I'm now going to talk about what my group is trying to do. Okay, pictures have shifted around a bit. Never mind. So what my group is doing, we called our project microscopes because what we decided to do is develop a bioassembly. So something that will literally activate on something using a promoter, travel through, and then result in some other action. That might be useful.
Someone was trying to get in and they found only half the door open.
Get in. I know that's something else I'm going to be coming on. But point is, what we were thinking originally was use it for water testing, which is why there's a picture of cholera on there and all the treatment plant. But we also realised we could use things like blood testing and testing for TB. The way it was working is due to a thing. Don't mind that. The way it was working is using the single CPX hardware. So what we did is we took the section of these, as I said, this one of the promoters from before. We went, okay, we'll attach it to an RDS because it's just what you have to do. It's like opening brakes in a computer program or something. So promoter RDS. The next thing we have is an IMP, classification protein. So that's this thing down here. Then an SI4 and terminator. So SI4 is a silicon binding unit. All that this bit does is it says, bacterial cell that we put this in, E. coli in this case, produce this thing down here, and it literally pops out a protein with a binding site on the end. This binding site will bind to silicon, so we've got a silicon B. And obviously this is on the surface. Great, fine, so I've got a bacterial cell that binds to silicon. What's the point? Well, there's another handy metabolic pathway involved, called the CPX pathway. It's stress activated, specifically for membrane stress. So you can imagine that if I've then got a thing sticking out of the membrane, and it binds on something, that membrane is going to suffer a certain amount of stress. It's going to evolve something on it. So it should activate this thing called CPX pathway. So what we did was we inserted something else into that CPX pathway. So we've now got another promoter here that reacts to the CPX pathway rather than binding site. Then GFP, which is green fluorescent protein. You will see it a lot in any project we've done. It's one of the easiest things to work with. Very handy because you can optically recognise something you modify quickly blows. It's a wonderful thing to do. But the point is, that now what happens with our beagle is if it binds to silicon, it stresses its membrane surface, and then after a cascade of different reactions going on, it starts glowing because it's bound to silicon. It's literally got the point of going, I found something over here. It's a biosensor. What's the idea of this? How feasible it actually is a different matter, but it's something actually they can do. So, for one, they are glowing. I feel we can point that out. They're definitely glowing. Here's some that are glowing with the UV, and this is from a fluoroscope image. In fact, it's a fluoro air pen, where the heat is air density coming in. What we're trying to do there is move in and poke the bacteria, because it measures the force required to trigger off this pathway. It wasn't overly successful because they're a bit squishy and tend to fly away when you do it. So we need to find a better way of securing them, but that's up to teething if you go. But you can see that all of these are fluorescing, so they definitely do fluoresce. The problem we found is they maybe fluoresce too much of them. So they're constantly being stressed by their environment, which isn't the best of things. What we do. But this is just one project that we do with iGEM. So we're now thinking, well, what do we do? Well, we take a few measurements and things. This is real data taken this week actually. So this is Triton X, which is basically a stringent determinant, so it should cause the cell to break down a little bit. So you see different concentrations, different things happen. So this is measured fluorescence. So a very low concentration, it's a bit noisy. Then we get the high concentration, it's got mental. So this is probably the cell breaking down and getting very stressed out, and then eventually it goes absolutely off the chart and dies. So we know that we're going to sort of indeterminate and things like that. But that was interesting for us because we need to be able to figure out how this part was working. But when it comes back to the rest of what is happening with iGEM, you also need to be able to characterise other things. So you can tell people how well the system works. There's no point in turning up and saying, I've got this bio device, it'll do this, without being able to prove that yes, under temperature it's stable, for example, which ours isn't at the moment. We need to work on that one a bit as well. But the joy is, with it being synthetic biology, there's ways around this. There's other people that have biobricks that might be able to solve this. There's other things you can do, sort of direct evolution. And there's also different methods you can move on. So we're hoping to do that in our next steps. The problem is, with it being a year of being us being undergraduates, we kind of run out of time. So, much like this, running out of time, I'm going to bring it to an end there. But roughly speaking, this is what I know all about, and it's the idea of trying to get a DIY hackspace set up or something would be good as well.